nanohub.org.
Online simulation, and more for nanotechnology.
So we'll get started with the folks we have here. I'm sure people will be joining us as we go along. Welcome to those who are here. And this is our NETS workshops. Today's, this is the 8-segment workshop that we have here. Today we'll do sputtering, one of the deposition series 2. You can see there's 4 deposition techniques that we're covering here. And this is sputtering that we'll be covering today. Next week we will be, actually Terry will be covering CVD. The week after that, Ozgur will be coming back and he will be doing ALD. I think he's doing it in partnership with Rich again. And then during the final week, we have Dr. Fatma Pur from Massachusetts Institute of Technology. In addition to, I think his name is Greg. I think is his name Greg from Stanford. Greg,
yep,
Greg from Stanford. Yeah, and they're doing confocal microscopy. So we're doing a coastal microscopy there on that last week. So you can see what's coming up and see what to look forward to over the next several weeks here. This is today's sputtering nucleation of deposited materials. And you guys know Ozgur. He's the he's assistant professor at Penn State in our engineering science and mechanics and a part of our Center for Nanotechnology Education and Utilization center. Okay. And you can see here that our clean room dude is going to be coming to us from Williamsville, New York, and that is it actually says Erie, New York. It's not Erie, it's Williamsville, I believe, and that is Rich Hill. You've talked to him before. If you've been to any of our workshops, you've seen him. Well, Ozgur can now get started with his material.
All right. Yeah. Thanks for coming again this week. So Rich and I will be going into the discussions about sputtering, which is another deposition technique. And one thing I should say before we start, so I wanted to make this a bit more colorful compared to the previous year's presentation. And while I was trying to do that, I didn't have the time to upload the previous year's presentation as a supplemental material. But you will find that as soon as we're done here today, you will be able to go to Canvas and look at what I was calling a little bit of a drier version of this presentation. What I tried to do was try to make it a little bit more interactive with some simulation tools that I will try to introduce to you. Up to some extent, you might use if you find them useful, of course, within your classroom, and that makes it a little bit more, especially in these COVID environments, a bit more still kind of quasi, I would say, hands-on rather than just like, you know, lecturing, regular lecturing. All right, so let's start quickly. Let me put this away. All right. Okay, so we have an outline. What I will try to do is I will first try to go over the plasma physics, because sputtering starts with plasma. We need to understand what plasma is. I'm sure you guys are a lot familiar with that. What I'm saying is like just to show you a couple of other ways about how to introduce plasma to the younger folks, just like suggesting these methods for you to adapt into your courses, of course. And then once we have the plasma occurrence, then we will see how the ion bombardment will be used to do the sputtering for our purposes of deposition. And later on, we'll look into like how, okay, so we've done the ion bombardment. We will try to see how those atoms, how those atoms that we kind of took away from the target are landing on the surface, how are they depositing on the surface, and how are they going to form, at what level, or what kind of a performance are we going to get out of this kind of deposition. That's going to be the next question. Later on, we are going to start talking about nucleation, just one lab that we can focus on within the main frame of sputtering. And then at that point, we'll be connecting to Erie, because Rich will show us the demonstration, the hands-on experiment for nucleation. Right, so like I was saying, And the lecture notes will be uploaded there too. So in order to obtain the sputtering, in order to do something about like use a sputtering method, we should first attain the plasma itself. And we all know that plasma is the fourth state of the matter, and we are reaching this fourth state by applying energy each time, right? So from the solid to the liquid, from the liquid to the gas, from the gas to the plasma, we're giving in the energy in order to, for example, in here, to make the atoms a bit more relaxed. And then later on, we'll need to give this additional energy to actually spark the plasma, to ionize the gas this time. So the main difference, as you can see here, that we had the neutral species here of the gas, the normal ordinary gas atoms. Now we have like these kind of charged particles. It's a charged soup. So a lot of the time when I hear about plasma, people say it's an electron soup, it's a charged soup. So they call it the plasma like that in the terminology, especially the clean room guys call it like that. So we already have plasma occurrence a lot. If we like leave the human-centric view in our universe and look at the occurrence of the plasma in the whole universe, we see that a lot of the time we have the matter in the plasma state. In order to obtain, and that's why we kind of see the plasma occurrence in many other cases here too. But like we were saying, we have to, from outside, we have to apply this certain power to break down the gas, to ionize the gas, to tear it into these electrons and ions. All right, so how is that going to take place? So we start with the electrons. So I'll just start with the regular, the dry format that I was saying, but then I will switch to this more colorful simulation tools. So we start with the electron, and let's say that this is A is our gas particle, so gas atom. It's going to be argon, by the way, today. And we'll, of course, discuss why we need argon. But the electron is here. We're going to speed up the electron up to some extent, and then we're going to hit this gas atom at that speed so that we will deliver the energy and try to knock off an electron and set it free. So we will start with one electron, and then we'll generate another electron. So that's going to make a secondary electron, as we were calling it within the discussions of SEM as well, the secondary electron generation there. So of course the charge should be preserved, the total charge should be preserved. So we start with one minus charge and a neutral species. So we should end up with a -1 charge, right? So we have like a plus ion and 2 electrons. That's going to add up to still -1. So that's one way of visualizing this ionization process, the electron, when it's speeded up. So we need to give this external energy, right? So that's what I was talking about. Once it reaches that speed, it's going to go into this slab. We can think of it like in an abstract way. We have like these gas particles, gas atoms. When I say particles, you understand what I mean. They are like embedded into this slab. And then in the vacuum space, that's what I mean, inside the chamber. And when the electron is like going through the slab, it's going to be likely to collide with these gas particles. So under certain restrictions, of course, like there is like the correlation between the interaction area, right? So like this electron and this gas atom will interact over this gas particle interaction area, the cross-sectional area, in which the nucleus will have some interaction, will be changing the trajectory of the incoming electron, and we have a chance to get the secondary electron free too. So that's going to be called the ionization for that purpose, but that's not only option. So we might have other options too. So this electron comes and collides with this atom. Let's call still that being A, but it may not have enough energy to do this full ionization. So we jumpstart the electron from some state, but we do not necessarily bring it up to this ionized states or set it free, okay? So we might get this electron to an excited state. So let's now switch to that simulation thing I was referring to. 1 second. And you can find these, you might have already come across these. This is from University of Colorado. They have great apps. And I will upload them to the website too. I'm using a lot of their applications, so this is just one of them. And it's the quantum well. I'm using this especially for the community college students because they're not like, they haven't seen a lot of quantum mechanics before, obviously. And it might be a little bit difficult, especially if you're not familiar with the concept, or even like these from the 4-year degree students too. They kind of know quantum mechanics, but they have never like thought that that's what they're using, quantum mechanics. Whenever someone is taught at the high school level, whenever they start saying 1s2, 2s2, that's quantum mechanics already. We have like these orbitals, we have like these quantum states. They know they're not aware of it, but they are using quantum mechanics. Okay, so how can we make use this this simple application? So this is a quantum well. What it means is, I hope you can see clearly on my screen. It's not the greatest choice of the colors, but this is the purple well here. So what that means is we have an area, a point here where we have a loss of energy all of a sudden. So normally everything is flat in terms of energy, and all of a sudden there is this well, as the name implies. This now there's a rectangular well. That means the energy here is, we can accept that to be a reference point. It's 0, and we have like this, like for the students' sake, for them to visualize it, we have like these barriers, like the kinetic energy, potential energy, those kind of discussions. So the whatever we have here won't be able to go up the hill easily, right? So that's the idea. So we can visualize, and I always got good results out of this when I start talking about, okay, all of a sudden, like a single atom to the combination of atoms and into the realm of like semiconductors, etc., and band diagrams. Instead of like going into deeply into the band diagrams, I of course start with the simple one single atom, and the abstraction of that atom representation is generally done by a quantum well, because it's so simple to visualize. What happens is, when you have this kind of a scenario with a quantum well, that kind of represents your atom already. So what do I mean by that? You have like this well where the electrons are kind of like, if they're trapped inside the Coulomb attraction force of the nucleus, they're kind of trapped around the orbitals, right? So they're kind of trapped in a well, if you like to think about it. So the ones at the lower shells, lower orbital, right? They're closest to the nucleus, and they will have like the smallest energy, and that's kind of going to represent that kind of district energy level here. That's the next orbital, that's the next orbital, goes on like that. So we can make this kind of an abstraction for them to understand it a little bit better. So you see, like we can say that, okay, so this is kind of like the outer shell, so we're like in the valence state. So these are like lightly bound to the to the nucleus, because there's a little bit of, just a little bit of a push will get this electron that is sitting here at this energy level be free. Just a little bit of a jump, and then it's going to be free. So this electron will take this kind of a jump, and as you can see, of course, like we will have like these kind of, when we come down to the core electrons, it's going to take a little more than that, of course. So what's happening is, say an electron that's sitting in here in our sputtering discussion is going to be knocked out by an incoming electron that has enough energy. So what's that electron going to do? It's that electron will transfer its energy, some of its energy, to this electron to set it free. What kind of energy are we talking about? Well, that's going to be to set it free, of course, it needs to go, I mean, this is an abstraction. This is just a quantum well, but we need to fully ionize that. But we can say that, okay, so it's going to have to go over this little hill here, this little separation. So it's going to have to transfer that much of energy to set that electron outside of the state. And we can tell to the students that, okay, so these are discrete energy levels. The electrons, as you guys already know, from even like high school chemistry, they will be like in a discrete state. So they can't just get some random energy and cannot be like in a continuous band, cannot just say, okay, I'll get just this energy. This is what I want. By the way, just interrupt me anytime you like, and then we can discuss a little bit in more depth. So the main idea is to do more interaction, like I was saying. And that's the energy that we will transfer, and that electron will be set free. But what happens if this electron that's sitting here is just kind of like jump started to like, or just going up to one of these energy levels, okay, just going up the ladder. We just give that much of energy. How can that happen? Well, the initial electron may not have enough energy to ionize this or let it jump over this barrier fully. It might just kick it to upper state, okay? So that's like another discrete energy state. So what's gonna happen? Well, in that case, our electron there will not be steady, right? The atom itself will not be stable. So that's going to be it's not a steady state solution. It's because that electron cannot reside there for eternity. And that's going to come down again back to this original level, all right, and fill that vacancy one more time. And that's what we are going to call that whole phenomena excitation. So that electron will just go up the hill to the next energy level and then come down and relax its energy. But I use that word, that's an important thing, relaxation, because we just use that incoming electron's energy to jump start it from this level to this level, okay, energy conservation ways. Okay, I did some conversion of energy from the incoming energy of the electron to get it to here, but then this comes down. Where's that energy gonna go? Well, that energy needs to be also dissipated, right? Or like should be used, because energy should be conserved all the time. So that electron, when it's coming from this level to down to this level, will transform its energy into emission. What's that gonna be? Well, that's our good, well-known plasma glow. We're gonna get see that we're gonna get a glow from the plasma. We're gonna see a generation of colors forming inside the plasma. That's coming because now this electron that's now here will come downstairs and land on that vacancy that was initially allocated, where it was initially allocated. So that's additional energy. That gap should be conserved, like I was saying. That needs to be converted to some excitation. Some glowing will happen, and that's why why the people in plasma physics, or when you're in the clean room, they are always like looking at the plasma color, right, for the emission. Right, so that's the excitation, as I was saying, and that's not going to be the stable solution. So we're going to relax it very quickly. The electron will come downstairs again, and then will be used to emit some photon, some emission of like light will come out of that interaction. It cannot be that easy for more complicated systems, like Terry will talk about it probably next week, but we might have not just a simple like argon as our A atom here, we might have like dissociation process. So we might have like compounds of gas, okay? So we just worked on argon so far, and we will do that today, but it might be like other gas as well in our general form. And why is that happening? Well, because we may not be just like, we may drive some chemistry. In our case, in sputtering, we're trying to limit the chemistry, but we may drive chemistry next week with the chemical vapor deposition, especially plasma enhanced chemical vapor deposition. In that form, we might need to dissociate the plasma, the initial gas that we're starting with. All these things are possible. I just gave them here. And one other thing, the students always fail into that trap, that when I talk about this ionization, this electron soup, everything, they think that, okay, so these charged particles are occupying like a lot of the, in terms of percentage, a lot of the whole thing, right? So they think that, okay, maybe the 50% is like these charged particles. Actually, that's wrong, we know it. So these charged particles will be less than 1% in the overall, the neutral species that we have, the gas particles that we're feeding in to the system to do the deposition, the sputtering. So this all ionized gas plus the electrons, all those charged particles will be a very much a little bit of a minority in the whole combination. All right, so don't worry about this graph now, but this is what we're going to work on with simulations. We're going to try to spark a plasma together with several different scenarios, but this is how it's going to work out. So we're going to feed in a gas, and that's always, I'm saying, argon, that will be argon. We'll use a pump. Why are we using a pump? Well, we're going to have to ignite the plasma, and yes, so plasma can be ignited in different conditions too, but in order to make it reasonable for us with a reasonable power supply that we're going to use, and also to make things much cleaner in terms of the cleanness concept that Terry had covered in his vacuum talk in the previous weeks. So we need a pump as usual. So that's going to be our confined chamber. So that's going to be the concealed chamber where the plasma will be there. And plasma is not the most beautiful thing for human health too. So that's also one of the things why we need to confine conceal the plasma. There's lots of those chemistry happening, and a lot of radicals, all those things are free radicals are generated. And then the third thing, so gas is one, pump is the second, the vacuum, and the third thing will be the outside power. And when we have that all together, we're going to be able to ignite the plasma, hopefully under certain conditions, of course. And what's going to happen is the following. So just for now, let's just look at it at this point, up to this point. So we have an initial electron, and that initial electron will collide with an atom. And then it might be an elastic process. What I mean by elastic process is that there's no real change of like energy or transfer of energy from the initial electron to the atom to ionize the gas. So this is an elastic collision. So that means just like bouncing back and forth without doing much of energy give and take. And then when we have a chance, so that might be just another one. And then you can think of like these things happening billions of times in just 1 second. So it's going to add up to quite a substantial amount of charged particles. But when we have the chance, so this can be now ionized. This gas particle will be ionized. The electron will finally do its task. That's what we are aiming for, and will ionize the gas and will set another electron free. And then you see it's going to branch out. So this is going to be the new journey of electrons now, and that's going to be the new journey of the incoming electron, the initial electron. And they're going to continue doing this. So as we go along, from our we're going to call these with special names, etc. But let's say from the first electron, that's where we're going to start our journey, and we're going to end our journey in the second electron. And I always give this analogy, and students, I guess, like it a bit. It's like the journey of Bilbo Baggins, and the poor electron will go through a lot of these little adventures along its way. So it's going to do lots of different scenarios, go through a lot of adventures, and continuous journey in the other electrode. While it's doing that, it's going to add up to a lot of electrons, as you can see, and a lot of ions. So it was one initially, and there we go. It's becoming two. You see another one is generated here, another branch. So we add up to a lot of electrons. But all of that will be taking place thanks to the outside voltage power that we're going to be also applying, and also the pump, the pressure level. So this is kind of always like said to be like a diode kind of scheme because of for those interested, it's just additional information, but we have a voltage distribution, a voltage and current graph here, an IV graph, like the electrical engineers call it. It looks just like a diode graph for those interested. So that's why it's also called a diode, like a scheme. And what we're going to do is, so the first thing that these clever students will immediately tell me, okay, but how about if we run out of electrons? Okay, so what's going to happen? Yes, so we have to self-sustain the plasma. So that's the most important thing. So what I mean is, at some point, we have to break down this gas and ionize this gas and form these charged particles. And this whole process will be self-sustained. Okay, so it should not immediately depend on the immediate outside voltage for, there will be some, of course, a huge dependence because of the guidance of the outside voltage, as we will see. That's what we're going to call the electric field, external electric field, but those are details, of course. The important thing is we're going to have enough electrons so we will not run out of the electrons. That's a very valid and good question that can come out from the students, and that's going to be sustained by what we will call the secondary ionization process. That's going to take place like this. So we will have the ions we will generate ions like we were saying here, and those ions will help us to get more electrons free from the cathode side. So I'm now starting to throw some more terminology here, so I will stop at this instant because I think it will be better to switch to the console. This is not, unfortunately, this is a licensed software, so if you do not have the license, it won't be easy, but at least for the sake of our understanding, it's a quite useful tool, I would say, for sustaining the plasma, for discussing the plasma. All right, so here we go. So this is what we're gonna do. Okay, so this is our little chamber. It's gonna be a two-dimensional chamber. We're gonna tie up one side, one electrode to ground. That's the normal ground that we know. And then the other one, we are gonna apply some voltage to the other one. So in this frame, of course, we have this being more plus than the other one, right? So that's why we're gonna call this to be the anode side, and this is gonna be the cathode side. Cathode being the negative side, anode being the positive side, okay? And we're gonna try to trigger the plasma inside with different scenarios. Yeah, this software is using like these complicated equations and doing some meshing computationally. These are called drift and diffusion equations. This is like just to say it loud, we have like the electrons getting emitted into the plasma and they're diffusing, but also they're like this drift under the influence of the external electric field. So that's why it's called drift diffusion equations. We're not gonna go in any of those, of course, but I would like to show you a couple of other things here. Yes, so this is the thing that I want to show you. So this is our chamber. This is gonna be our chamber. That's what I'm gonna show you. And inside we will have the electrodes. So I will only be able to show you like half of the chamber because it's going to be computationally identical. So that's why it doesn't take the whole thing into consideration. But I want you to imagine that it's the full chamber. So I'm just going to show you half of it, okay? And we're going to do our simulation accordingly. So one thing, we're going to feed the, of course, this chamber with argon, like I was saying. And let's look at the possible chemistry that can take place. So we've got another. Yes, definitely, Rami. So this is something I can do. This is generated by Comsol, but I can definitely send this to you. It's available on website and their website too, but I will upload them as a supplemental file. So we have an electron that can be just going through an elastic collision. Like you guys can see what's going on. This will, like from input to the output, there is no required, there's no in and give and take in terms of energy. So the delta E, the epsilon is zero. No energy is required to do that, just like bouncing and then changing its trajectory. That's it. That's the only interaction. Now, what's going on in the second case? We have electron colliding with the argon, and then we're doing the excitation, like I was saying. So this will require 11.5 electron volts. So when I say electron volts, of course, students are like, what is electron volts? And then that's when I say, like, think of joules. We are all familiar with joules, of course. Now, in this realm, when we go down to the electrons realm, this is like their joule, the energy unit of electrons. And this is going to require 11.5. So this is another reaction that can take place. Electron can collide with the excited argon. Why not? And this might basically take it back to its original situation. So it's going to be the normal ordinary argon. So this is going to just like not require energy, but this is going to be the emission that I was talking about. So we will not require energy to drive this chemistry. It's going to be the other way around. So we'll release energy. That's why it's getting minus. So what else? We have the proper ionization. We have one electron colliding with the argon. We're generating another electron and we're generating the ion. So that's going to require more, 15.8. More than what? More than the excitation. Look, that was 11.5, right? Another chat thing came. Of course, yes, Remy, thank you. And another one can happen like these kind of ionization processes might be happening. Like we can ionize the not fully ionized, but excited atom of the gas. So that's going to take less energy, 4.24. Other things are also happening. Just wanted to talk about the chemistry that are available. Now let's run the simulations. Okay. Now we're hopeful. We go to the lab and we try to ignite the plasma and for some variables, for some situations. So yeah, so for those folks who are not familiar, don't worry. I'll just walk through, just look at what I'm showing you, okay? So don't worry about the rest of the complicated, crowded material that's shown here. So this is, these are the variables that will be of interest for us. So this is mobility, will not change this, but we're gonna change the applied voltage. So let's just take it to 100 volts, or maybe just start with 10 volts. Yeah, why not? So we're gonna start with a 10 volt separation. So what does that mean? So we're gonna still ground this electrode and we're gonna apply 10 volts to this electrode, okay? So just then 10 volts. And we're gonna feed in argon, that's the gas pressure inside our chamber. We're gonna feed in 0.5 torrs of argon, okay? That's it, why not? That's kind of huge amount, I know, 500 millitorrs, but we're gonna feed in with that. And let's go to geometry just to make sure. Yes. So this whole chamber is like 0.4 meters in total. So from end to the start. And we're just going to simulate this very quickly. So you see it does the meshing and it just does the computation. So we just applied 10 volts and we're going to ask ourselves, are we going to be able to break down this gas? Are we going to be able to bring it to the fourth state? Are we going to be able to deliver enough energy to the electrons? That's what we're trying to do, right? We're trying to generate some guidance, some external power for the electrons so that they can collide with the atoms and then ionize the gas. By the way, I'm speaking because all of these simulations, each one will take like a half a minute. So during the passage of time, we can also try to remember what we just reviewed. We're going to try to ionize the gas. That means we're going to require some external energy. Are we going to be able to do that with only 10 volts? So this is the results parts. Like I was saying, it's kind of crowded. Don't look at other things, just follow my lead. Let's look at the electrical potential, the one-dimensional potential. All right. Okay, so this is showing us in terms of the x distance. What is x? X is this, along this axis, just like along this vertical axis, from one electrode to the other. I start with 10 volts. I generate these, like this voltage distribution, okay? And I end up with 0 volts. Did I generate, or plasma, let's look at the ionization. So this is argon ion number. So let's look at the numbers, 3.5, 10 to the 11 per meters cube. So first signature of plasma is that we will have a significant ion numbers here. And this is not good enough. So it may not be obvious immediately because you might think, okay, what is a good enough number? This is, let me tell you, gonna be like 10 to the 4 times smaller, but we will see along the way. And let's look at the electrons as well, electron density. So again, electrons, we don't have enough electrons as well, 10 to the 9. So that's going to be also a small number. But one immediate signature is the this potential value. So there is nothing really happening in here, as I will show you more in depth, the special features of a plasma generation. So it's just coming from 10 volts to 0 volts, that's it. All right, so you will see what I mean when we generate the plasma. This is going to be really drastically different. So let's just say 50 volts. Now I'm going to apply 50 volts. What am I doing now with applying 50 volts? I'm just assigning this top electrode to a higher value. Why is that important? Well, let's go back. When I apply that to be a higher value, this voltage power to be a higher value, we have like a, I'm sure everyone must have seen that, we have like a parallel plate scenario. And that parallel plate will have, once you have a voltage distribution between the plates, will generate an electric field. Electric field is important because electric field is the immediate thing that will be converted to the force, E times Q, right? Whatever the charge is, Q, electric field is electric field. Once we multiply the electric field with the charge, then we find the force to guide these charged particles. That's very critical because we need to give this electron, this poor electron that's starting its journey, Bilbo, we need to give that enough energy to do the whole ionization and to survive to the other side. If we do not give enough energy to the electron, this poor electron, initial electron, that's not going to be able to do that. It's not going to be able to generate all these electrons. So their population will be really not very significant. So it's going to be fatigued, okay? Before it goes to the other side, it's going to deplete its energy, and it's not going to be able to, like we were saying, self-sustain the plasma. All right, so they will run out of electrons, kind of. You can think of it like that way. So, all right, so now, not this one, yes, this one. Remember, it was like 10 to the 11, right? So we're still in that range, 10 to the 11, the generated ions. And the electrons was like previously, it was 10 to the 9. We're still in that range. So there's not much of a change still. And the electric field potential is kind of like similar. Look, we're starting from 50 volts and then we're ending with 0 volts. I can't use this for my sputtering, and I will tell you once we run it for the final value. So let's now switch to 100 volts and run this simulation one more time. So when I give it to 100 volts, I'm going to be able to speed up the electrons at a much higher speeds between these two electrodes with the applied voltage here, not just to break down the plasma, just to generate the plasma, but for my purposes of sputtering too, because sputtering will require me to attack the target. So I have the target material here. I have the argon ion, the generated argon ion, right? Where's that going to go? That's going to prefer to go to the negative side, relatively negative side, okay? So that's going to go there, not to the anode. That's going to go to the cathode side, right? So the negative side. And it's going to go there and attack the target to knock off particles from the target, okay? In order to do this, I have to give a sustainable, substantial energy to this argon ion. All right, so, okay. Now this final simulation has been ended, so let me show you what I mean by this. Now this is for this case, okay, right. So this is an immediate signature of plasma generation. Now let's look at the voltages. So we have given 100 volts on this side, and it comes down to 0 volts. Why is this important, or how do I know that I generated plasma? There is a side, you will see, that is kind of like a constant, almost like a constant column voltage. We call that the plasma column, okay? So that's kind of like, there's almost like 0, of course, it's kind of like going up and down, but the voltage change is like not super large there. But at this point, there is going to be a cathode fold. So this is the cathode side, the 0 volt side. This is the 100 volt anode side. There is going to be this little portion here where we are going to be having a huge, like a waterfall. That's the signature of the plasma. We're going to have a huge immediate voltage change from 100 volts down to 0 volts. Why do we need that? We need that to be able to attack the target efficiently. So we're going to place the target here, and this is going to be like roller coaster. Once the ion is generated inside the plasma, the electron will generate the ion. The ion will come down and literally just put a little roller coaster in here. It's going to be like, ooh, coming down and attacking the target area here, because this voltage difference will give the ion enough energy to attack the target side, to knock off particles, to knock off the target atoms from within the plasma chamber, within the sputtering chamber, okay? So finally, we were able to get a self-sustainable and good plasma trigger occurrence inside our plasma. How did we do that? We just had to apply a higher voltage value. 100 volts gave us that. Now let's look at the ion numbers. Right, like I was saying, immediate signature of plasma occurrence. Yes, it's a very small, I'm sorry about that. Let me, maybe I will try to see if I can, nope, I can't do that. It looks like I can zoom into that, but this is 10 to the 15, okay? Remember, it was 10 to the 11, right? So this is like 10,000 times higher. So we have a lot of ions right now comparatively. And where are the ions generated? Ions are generated like around here, okay? Position-wise, it's also important, okay? Let's keep that in mind. The ion generation point is kind of going to be coinciding with the electron generation. So I just jumped to the electron generation. I didn't change. This is a new graph. You see, electrons and ions are kind of happening around the same value. Why? It's this reaction. Let's look back to the reaction that we were talking about. One electron came in and generated another electron, but at the same time, we generated an ion. So where we're generating more ions, we're also able to generate more electrons. So it's kind of like a harmonious, it's working in harmony. Okay, sorry about that. And what else? So in terms of the electrical potential, so again, another signature of plasma occurrence. Look at this, the column that I was talking about. Almost no potential change. This is the color code. And here we have a huge drop. Do you see that? A huge drop, very immediate. This is where we place the target. So the target will be here. And this is the positive side, of course. So the ions, once they're attracted to the negative side, they will be like seeing this immediate change, and they will be like, ooh, this is just like a roller coaster, or the, you know, the waterfalls when you go to the Luna Park. I love them, but I also hate them. They're so steep. It's just like that. You're an ion, and they just like fall down to the hill and then attack the target immediately because of this huge change here of the potential. And then there you go. You just knock off some particles from the target. And where are they going to go? They're going to go and land on the other surface, right? So that's how we do the sputtering deposition. By the way, so I'm going to be leaving some of the drier lecture parts to the supplemental material. So I'm going to be jumping over those, but they're already going to be given in the supplemental part. So I'm kind of emphasizing these scenarios a bit more because that's what's lacking in the last year's presentation. But if you go to the other, if you have interest and time, of course, to the supplementary of the previous year, you can find the more like drier version there in terms of the presentation. All right, so we were now able to generate the electrons and the ions. Look at the electron generation. It's closer to the cathode side. The electrons just kind of like start its journey and it gets accumulated. It's speeding up while it's arriving to the anode. This time it's not going to be fatigued, and it's going to generate more sisters and brothers along its way, and it's going to add up to more electrons here. So there's more chat coming up. So let me see. You can change the size of the shaded screen by going to the top view options. Thank you, Rana. I'm not sure if that's going to be available with this console thingy. That might be about that. Sorry, I'm not sure if that will be. Oh no, what I'm doing something wrong. View options. Oh, I can zoom into certain regions. That's what you're saying. Oh, okay. Oh, sorry, that's not for me. I see. Okay, complete misunderstanding. I'm sorry. All right. So one other thing. If we generate the plasma, they're going to be found mostly around the cathode, like I was going to say, and the ions are also kind of going to be found there. And what about the excited argon? So this is now the excited argon. This is not the ionized argon. Okay, so this is the excited argon. Look at the population, 10 to the 17. It's even closer to the cathode. Okay, so it's like, look at the other one. It's now a little bit further away. And this is now here. Why is that the case? Why do I see the excited argon closer to the cathode compared to the actual more ionized argon? I mean, in other words, why is the ionized argon a little bit further away from the cathode? And why is the excited argon closer to the cathode? the reason is, let's go back to the Bilbo Baggins journey. The electron started its journey here, but it doesn't have immediate super high energy. It's ramping up as well. It has some initial jump up because of the ion that just gave its energy. But the first, when it's closer to the cathode, it's going to go into collisions. But these collisions will not be able to ionize the gas efficiently. All right. So instead of doing that efficient ionization, it will do more. It will not have enough energy to ionize the gas efficiently. So it will need more time and more space into the plasma to be able to ionize the gas more. Does that make sense? So it's going to cover more territory to speed up and to yield more ionization rather than excitation. Makes sense? That's why excitation takes first, and then the ionization goes on. But then after the ionization, it loses energy much. So people call these areas to be dark areas, dark sheets. That means the electron has consumed a lot of its power, so it's not able to do glowing. So it may not have enough energy even to do excitation. So that's why it's called dark areas. Does that make sense? So let's remember there are a couple of scenarios. So we can either excite the atom or we can ionize the atom. But what if we don't even have enough energy to excite the atom? What's going to happen? Well, that's going to be the dark area. Makes sense? Because we're not even glowing. We're not able to excite the atom, the argon there, right? So that's another reason. Or we might be doing a very efficient ionization and not doing any excitation. So that's another dark area. So it depends on how much of excitation we are able to do. If there is not enough excitation inside the chamber, those are going to be darker spots. You won't see the plasma glowing in those areas. Okay, so those are going to be the dark spaces. All right, so we've done these three scenarios. Now let's go and do a couple of more. All right, so now I'm gonna tune down the pressure here. I'm gonna say 0.05 torrs, and I'm gonna be, yeah, we're not flowing in enough gas right now, like we were doing. Not 500 millitorrs, but only 50 millitorrs. What's gonna happen? Let's see. Let's rerun the simulation one more time. Yeah, now inside our chamber, we have, ratio-wise, 10 times smaller amount of gas. So what do you guys think? What's going to happen? Are we going to be able to spark the plasma or not? Yeah, Kendra says no, probably. And yeah, so that's why I added here for you guys to see. If you do not feed enough gas, there won't be enough argon particles, right, to ionize. So, and there won't be enough electrons to generate as well. So we may not have enough particles to work with, and there we will fail. We won't be able to excite a self-sustainable plasma for these parameters, of course. I'm not generalizing this. I'm not saying with 0.05 torrs, you cannot do that. I'm not saying that. But look, now, once I look to the electric field potential, oops, not this one, look, there is no column, like I was saying, no, like the roller coaster effect. Remember the voltage was, this was like 100 volts, and then immediately it was dropping to 0, right, previously. Now we have like, we're starting with 0, we're ending with 100, starting with 100, ending with 0. There's nothing special happening here. It's just like almost like a linear voltage distribution. We weren't able to spark the plasma, okay? And the argon ion again dropped down to 10 to the 11. The population again, the density. I'm saying population, but you guys understand, of course. So we weren't able to do that. How are we going to counteract this? So I dropped down the gas to 0.05. Now think about it this way: the gas particles are really sparse. Like here, the electrons. Once we have electrons, they're just like going through them. There's too much of what we call mean free path. So they're not colliding. Does that make sense? To generate the secondary electrons, they're not able to find each other because we had like too many before. Now we have only like too sparse, less amount of argon. How can we still make sure that we will spark the plasma? I can do something else. I can increase this voltage, right? So let's increase that to 500 volts and let's rerun this again. So what's that gonna do? This is gonna do this. Okay, so I still have like sparse number of particles, but if somehow I find the particle, if I collide, it's gonna be very, very efficient because 500 volts means what? Higher speed of the electron, makes sense? So no more chances, no more, it's not left to chances. If it collides, it's gonna ionize the gas because I'm now guiding the electron with a lot more force to the anode side. So this ionization process efficiency will be enhanced, okay? Yep, now there you go. We sustain the plasma again. This immediately tells us the electron density is closer to the cathode. It's really high, 10 to the 16. We kind of counteracted the loss of the pressure. The pressure went from 500 millitorrs to 50 millitorrs, but we were still able to ignite the plasma. How did we do that? We increased the voltage to 500 volts. We applied a higher electric field, in other words. And this is the electric field, electric potential again. Look at the column. The column is here, and then the cathode fold is here, the roller coaster is here again. And the ionized argon population is really high again. So, why do people want that? Why do people prefer a lower pressure? Because a lower pressure means a better chamber, a cleaner chamber, right? And it will also mean a couple of other things too. So you would like to actually ignite the plasma and work with a sputtering tool that's going to come down to a lower pressure if you can afford it, of course. Like 500 millitorrs is really very high, our initial value. All right, so a couple of other scenarios that I would like to discuss. So let's switch to 0.1 torr here and our previous 100 volts here. First, I wanted to show you this. 100 volts, but now let's do the other way around. Let's now feed it with too much of gas, 5 torrs, okay? Just the other way around. And let's rerun this simulation. So now we have too much of gas, too many particles. Once the electron starts its journey, it's gonna see too many collisions, too many possibilities for collision. So it's gonna deplete its energy too. That's what I'm saying is, it's not a, that's also not gonna work out great for us because too many particles along our way is also gonna be bad for us as well. So as we will see, we'll not be able to ignite our plasma again. So 5 torrs will not be able to ignite the plasma. We'll just see the field distribution to be the not so interesting voltage drop, linear drop, like I was saying. So we have to think about like these different scenarios where the voltage versus the pressure, and also maybe the chamber size, I'm sorry, the D size here between the electrodes. All those are important and things to actually design in terms of the whole overall design of the plasma chamber. And that's called the Paschen curves. So they're very critical. They tell you like where you can break down the plasma. So what kind of a voltage is required to break down these kind of gas? Like you guys can see different gases used here. So if you're inside these curves here, you're fine. You'll be able to ignite the plasma. So these are kind of like given lookup table kind of graphs you can refer back to. So let's say you're working with one particular gas and you try to see the breakdown voltage that's going to be corresponding to a certain P times D constant. That's pressure times the D, the size of the chamber. All right, let's go back to the thingy. So you see the electrons are, density is closer to the anode, so we were not able to ignite the plasma. So let's look at the electric potential. So we start with the 100, it's like a linear drop again. We were not successful again, one more time, unfortunately. That's why we should not be considering higher pressure values to ignite the plasma. Let's look at other cases now, switching back to 0.1 torr, but we will do the following. So with 0.1 torr, we were not able to ignite the plasma. Let's just see that again with low pressure value. Yeah, so that's my little beagle kind of sleeping in the background. So if you hear some snoring, that's her, unfortunately. So in the meantime, let me show you these targets that we were always referring to. So these are going to be like 99.99% pure targets that we're going to use, like gold, like silver. We have a large variety of particles, targets that we can use. And this is the physics that we're going to now look into quickly. We're going to attack the surface. We talked about the plasma generation and how we can use that roller coaster effect, the voltage sudden drop, right, with the incoming ion. So we're going to use that ion to speed up the ion and attack the target to knock off some more electrons for secondary ionization, and that's going to be our main source of electrons, but also to knock off other particles from the surface. That's going to be our main deposition particle too. So those are our two aims, but we might have implantation and we might have other things coming into play too. We're going to see that just in a bit. Let's look at the scenario. So yes, with 0.1 torr, we were not able to ignite the plasma. Electric field potential is just ordinary 100 to 0 volts. Now, what can we change here? We can change the following. We can change the geometry. Now, this electrode to electrode separation is quite large. So if I make this to be 0.24 meters, so let's build this. So you see the electrodes are now very close in the proximity. And let's remesh this again. So in general, these kind of computational systems have to be remeshed, and let's compute that one more time. So what am I doing here? I'm putting these electrodes much closer to each other to compensate for the loss of the pressure. So this is kind of equivalent to saying, okay, so if I put them closer, I might increase the electric field between these two plates. So because now they were under an influence of an electric field because they were kind of far away from each other. These two electrodes were a little bit far away from each other. But if I make them closer to each other, the voltage drop will be drastically higher in just like these two electrodes that are very much close to each other. So I might give enough energy to ignite the plasma. I think this will not still be enough, but I have to be careful. So even though I make them too close and increase the artificially increase the electric field or artificially increase the external power that I apply to the plasma. Remember the voltage that I supply, that I give into the plasma. It's kind of like corresponding to the same effect, but there is also another scenario that's coming in here. The chamber size. The chamber size is very small now. The chamber size is very small. Once the electron starts its journey from the cathode side to the anode, it's going to cover a very small territory. And if it somehow knocks an atom, it needs to ignite the plasma. It needs to ionize the plasma. So there's a lot of force, a lot of responsibility on that electron's shoulder to ignite the plasma. So this is not, there's like a lot of trade-off going in here just for our discussions. So making the chamber size too small will not be in our favor all the time. Yes, you will be increasing the electric field, the voltage between these two electrodes. The felt electric fields on the electron will be higher, but since the journey is very small, right? Once we start the journey, we need to ionize the gas. If we collide with an atom, we need to ionize the argon. If somehow we are not able to do that, it's bad. It's not gonna work out. So that's why I think in this case, yeah, we were not able to again ignite plasma because there are a couple of other factors working against each other. So yes, this is a linear drop here. You see just from 100 volts to the 0 volts. This is where the second electrode is. This is where the other electrode is, just a linear drop where we're not able to ignite. But if we make this geometry, I don't have time to do that, unfortunately, but if we find a suitable point, like somewhere here, we might end up with this good geometry where the separation is still good enough to give us a good enough amount of like time for the electron to ionize enough argon, at the same time to give us good enough amount of electric field felt on the shoulders of the electron to pull the electron to the other side. So both things are happening at the same time. So there might be a sweet spot between these two the positions, these two positions, where we can have a good plasma ignition. All right, now we come down to the surface. We're gonna ionize, we have an ionized gas. We're gonna knock off particles from the surface. What are we gonna do? We're gonna use this other software that I will upload to Canvas. It's gonna be called SRIM. And basically, this is a free software, and a lot of people are using this software. You can download it. I will show the instructions for you guys to do that. Okay, so we come down to the target. Let's say we are using argon as ions, and we're going to look into surface sputtering. We're going to attack tungsten. We're going to attack tungsten of just 100 angstrom, 10 millimeters. And we're going to attack it with a moderate energy, 0.1 kilo electron volts, okay? And we're going to send, just for our discussions, just 1,000 ions. Okay, so it just puts it to the other side. But look what's happening. The argon ion is attacking the surface, okay, and trying to knock off the tungsten particles. So the tungsten particles, oops, the tungsten particles are going to be set loose. At what rate? At this rate. I know it's quite difficult to read these numbers, but let me read it out for you guys. 8.7 electron volts. So for every argon, one argon ion, we're going to lose a tungsten atom at a rate of like slightly above 0.2. So what does that mean? Every one argon ion will be able to knock off, set free 0.2 tungsten atoms. Why is that taking place? Because we're going to attack the surface from outside with external power supply, and we're going to try to counteract the binding energy of the tungsten particles. So those are chemically bound to each other, right? The tungsten elements are bound to each other. So up to this side, it's still tied up to the surface. That's why it's not sputtered off. But beyond this side, if the tungsten that is speeded up by the incoming ion, if there is enough energy that is delivered from the incident argon ion to the tungsten particle, and that reaches beyond that 8.7 electron volts in this case, we might have sputter off this tungsten. Let's look at it again. So that's that number, so 8.7. And you can see here the sputtering yield. That's the most critical number for us. That's 0.24. Again, what does that mean? Every one argon ion is able to sputter off 0.24 tungsten atoms, okay? You might say it's a very low efficiency, right? Yeah, I agree. So for different materials, it may not be so high, but now let's think about another even worse case. What is a worst case scenario for sputtering? It needs to be an element that has a very high binding energy, right? So I'm attacking this surface, but it needs to be a very high energy. What can that be? Like carbon. Let's attack carbon. Remember the sputtering yield of tungsten, it's 0.24. Now we're going to attack with argon again, but this time we're going to attack carbon. and with the same number of ions. Just these are called Monte Carlo type simulations, just trying to look into the trajectories of random walk trajectories. Oops, too much of energy, sorry. You see how much, if I give too much of energy, it does ion implantation. So that's why the ions went into the depths of the target, but this is not the case for sputtering. This is the case for ion implantation. So I need to give the ions some smaller energy, because that roller coaster, that's the energy here. That roller coaster will give us enough energy, this energy here, to do this sputtering. And I'm just giving 100 electron volts. So you see, I still have some ion implantation, but I'm also doing some sputtering. Let's look at the numbers. Yep. So this is the case. So you see, the sputtering yield for carbon 0.002. Of course, this is an exaggeration. This isn't going to be this small, but a lot of the times people ask when they're buying sputtering tools, can you sputter off carbon for me? Because the sputtering yield for carbon is kind of low, and that's due to all these kind of binding energies of the carbon elements, the covalent stronger bonds that we're talking about. You see, remember the other one, it was like 0.2, right? So this is like 100 times smaller with respect to the other one. But of course, this is a very small simulation. This is not the correct number, but just to give you an idea, like compare and contrast the different target materials and the sputtering yield. Okay, so that's again, the software is free. I will show you how you can download it. S-Stream, maybe a lot of you are already using this, and it's really nice to play with the students together to predict like the sputtering yields, etc. But the best sputtering yield will take place when the incoming ion and the target material are like close to each other, like in terms of the mass. So you see, when their mass is like close to each other, when M2 and M1 are like 1, then there is the most amount of momentum transfer to the other one to sputter off the particle. So these are the so they are covered in that drier version. So I'm going over this very quickly. You can look at them. Maybe you already know a lot of them already, but this is the sputtering yield that we calculated together. And this is the drier version, but it depends on a lot of things, of course, the mass of the target atom, the mass of the binding ion, bombing ion, the argon, and the kinetic energy. Of course, if we increase it, that's going to increase too. And the binding energy that I was talking about, that's coming in the downstairs in the bottom to drop down the sputtering yield. So people have looked into different gas and different particles, ions, to do the sputtering yield efficiently. So you see, every time they looked into 8A column gas, like argon here, like kryptonite here, like xenon here, they're finding a local maximum. What does that mean? The ones that are doing less chemistry but have full valence shell electrons are giving us the best sputtering yield. So we need to work with those. And of course, like xenon, kryptonite, like because of the reasons of momentum transfer, will give you better sputtering yield, but they are more expensive and not as easy to come up with as argon. So we're kind of sticking to argon. And of course, the sputtering yield might be increasing with respect to angle. Some of you folks who are familiar with billiards are already familiar with this. So it's kind of like that. I also tell that to my students. So if you look not with the direct angle, but give it a little bit of a tilt, so you might sputter off better, right? Yeah, that scenario. So I'm going over these drier discussions quickly, but now let's just discuss the evaporation and the sputtering before we go with Rich in like some like 20 minutes or so. So we covered evaporation as the first deposition that was in series. What was evaporation again? We're just putting some material inside our crucible and heating that up and trying to put that evaporated material on our wafers, right? That was also happening in a chamber. So the problem with this was it was always depending on the vapor pressure or the melting point of the material. So if you have a high melting point, that kind of was very problematic for us for the evaporation's sake, because we cannot go to those high melting temperatures with thermal evaporation. We had to switch to like E-beam evaporation and such. Another problem was, like, I'm just reviewing the problems from evaporation. The other problem was, like, we weren't able to do alloys very well. Like, you had to do engineering, a lot good engineering to do like these kind of very complicated schemes to do some alloy deposition with evaporation, like combining these two crucibles together and hoping that there will be some alloy formation here. But of course, you need to determine the evaporation rates, etc. It's very complicated. In sputtering, you don't have that kind of a problem. You can now do sputtering of alloys. And you're not temperature limited by the melting temperature. You can do melting. That's now another independence from the melting temperature. So, okay, so a couple of the intelligent students will ask, that doesn't sound reasonable. You just talked about the sputtering yield, and now I have two alloys, and I mean two elements forming up the alloy, and now their sputtering yield will be different. Now, not their melting temperature, but their sputtering yield will be different. Now, there's also now a segregation, not because of the temperature, but a segregation because of the sputtering yield, they will say. And I will say, wonderful point. This will balance it out each other. So let's say if you have a high yield material like here, like a low yield material is here, the high yield material will be deposited more, and then in the target, you will see that there's going to be left of less high yield material. So now the low yield material will take over, because the ions will now start to knock off more of the low yield material because of the low population of the remaining high yield material. So it's going to balance it out each other. We will be able to do alloys this time. What else? Okay, so Peter talked about the uniformity problem. So forget about these math. We don't have much time to go into those, but you can find more discussions in the supplemental. One thing to note, in the evaporation, we're expecting to find a nice, like a good height all around, but we never come across that because we have this kind of a uniformity problem where we deposit most in the middle. I just have a good simulation result to show you guys that that I had prepared for the students, and I will share this with you too. So this is a simulation result coming from the, can I see inside? No, I can't zoom in, unfortunately, but you can see what's going on here. This is an evaporation tool that's used like a bell chamber that Peter and Rich use. So you see there's a wafer here that's being deposited, and we're evaporating metals from here. So you see that we're depositing all around on the walls as well as on the wafer too. And as the time elapses, we're some accumulation of the material. Maybe this isn't showing you the best. Maybe we can look at this. This is the final result. At the end of the 60-second deposition of evaporation, we have the most amount of accumulated material. Yes, it is COMSOL again, Abdulali. So at the end of the 60-second, we have the most amount of thickness in the middle of the wafer. So I was just simulating for a quarter wafer, like you can see on a regular silicon wafer. So there's the most amount of aluminum deposited in the middle, like you can see. When what's going on at the edges, like it goes down to 35. It's just because of the selectivity of the deposition methods with evaporation. When we have evaporation, it's what we call a line of sight effect. So it sees the direct line immediately. It sees this with a tilted angle, so that drops down the deposition. You can think of it that way. Now, because of that problem, we had shadowing issues, especially like these patterns. So if you have a pattern, and if your material evaporation is here, that's going to be like doing these kind of shadowing effects, which are going to be bad. You can counteract this by some diffusion, by rotating and heating, and then this material will deposit and diffuse all around again. But instead of a single source like this, in the case of evaporation, we now can utilize a very large source. Our target is very large in the case of sputtering. So that's going to come like emission from all these different point sources. You can think of it that way. And that's going to like smooth out all that selectivity with respect to the position, okay? So it's gonna smooth out that dependence on the angle. So it's not a direct line of sight. So it's gonna be able to deposit more uniformly. But nevertheless, as Terry will talk about more in next week, chemical vapor deposition will give you the best results if you're looking for the quality of your deposited materials in terms of the conformal deposition. And I will talk more about it in the ALD more. So you see, just look at the parts that I'm highlighting. There's a little more information that you can find in supplemental. I'm just quickly going over these materials. So you have some thickness here in the sidewalls, and you have some thickness in the bottom here, the trench, right? So they're kind of almost like equal to each other because this is driven by chemistry. So surface chemistry instead of the ions coming down landing on the surface. So in case of evaporation or sputtering, those were physically driven forces. So they have some problems, like the sputtering can, because of its ionic bombardment and then the particles coming down to the surface, you might create like these kind of void structures. So those are really things that you have to tackle. People use like these kind of collimators to guide the incoming target material atoms to give them some directivity so that those voids will not be caused. You see, they're not targeted with this directivity, so you do not create that kind of a bad scenario, and then you don't create those voids. These are details. I'm going over these. There's like, of course, evaporation is good, but sputtering has a lot of better advantages on top of the evaporation. We have a wide variety of metals and a lot of materials that we can coat. We're not limited by the thermal evaporation. We end up with better film quality, as I will also talk more in the last 5 minutes or so. We may not be suffering from the X-ray damage that's coming from the especially E-beam evaporation. And we are using large area targets instead of the smaller targets that we utilize in evaporation. The disadvantage is we're using higher pressure, so it might be dirtier. And the deposition rates of some materials might be a little bit lower. And some materials may not be doable with sputtering because you're doing ion attack, right? Ionic attack. So that's going to be too heavy for the materials and it will not work. So yes, like I was saying, you guys will be able to find a lot of these details that I kind of jumped over for the sake of showing you more simulation results in the supplementary. So as an end result of our sputtering, we might have different various cases. Like we now have created the plasma, great. We have attacked the target, great. Now we're coming down onto the surface. How is our surface going to look like, right? So that's the question. So is it going to be good or is it going to be bad? Worst case, one of the worst case that you can have is like these kind of atomic shadowing problems. This is what's going to happen. This is also a simulation result from, say, 1980s or so. But what they're showing us in their paper is the following. So if the material that's set loose, this is now the material. Let me activate my pen. So let's start from the beginning. So let's put the cathode here. This is now the anode here, okay? The cathode and the anode. And we ignited our plasma. Plasma is somewhere here. We have the argon ions and we have the electrons, blah, blah. And the argon ions that have been generated are attacking the cathode side and knocking off particles. Okay, so let's say we're sputtering gold. Okay, and the gold is now coming down. But depending on how it comes down, and it's all the other things that it will see along its way, it might land on the surface in a very arbitrary form. Like this gold, for example, gold atom might just be shadowing the other atoms and might not enable, like previously we've seen the shadowing effect with the patterns. Right now it's an atomic scale of pattern shadowing. Well, how is that happening? Well, since the gold is coming mostly predominantly with this kind of tilted angle for some reason, we're not able to functionalize these areas. You see, there are gaps, there are voids, atomic voids. And when you do measurement, you assume that this is going to be your perfect good gold, but no, it's going to give you a very like a defect, full defect gold, or other metals as well. So it's going to be really degraded from the metal that you're aiming for. The resistance, for example, resistivity will be much higher if you measure the resistivity. So people talk about the Thornton zone model, but we're quickly going over that. But in the end, it's going to cause these kind of vacancies. The crystal structures will be formed, like you can see the vacancy. And those kind of vacancies will be very easy to be oxidized, okay? So once you have like these defects, let's say we're doing molybdenum that I do with my students here just to show this effect. The molybdenum's resistivity will increase and its conductivity, so resistivity, the resistivity will increase and its conductivity therefore will drop down because of like these kind of voids. And I will start seeing like these kind of grain boundaries. These are the boundaries inside the crystal structure. Like say I have a certain crystal orientation here, okay, crystal orientation here, and some crystal orientation here. So whenever these two meet, I have like this crystal boundary, like you guys can see in here. All right, so I'm just like giving a very abstract example here just to show you like these kind of crystal boundaries. Because of the stacking and how these deposited materials actually land on top of each other, we might end up with these kind of faulty sites. And what's going to happen? The electron that's starting its journey to conduct electricity will have to channel through these kind of crystals, different crystal orientations, and that will increase our resistance. It will add up to the resistance. So whenever it sees these, it will add up to the resistance. And we will see an improvement in terms of the resistivity, therefore. So these are called the grain boundaries. And inside the grain boundary, we have like a uniform, somewhat uniform crystal orientation. Crystal orientation meaning that these atoms are nicely situated in ordered, somewhat ordered fashion. And we can determine the crystal orientation based on the temperature. So we might tune up and tune down the temperature, and based on our performance, we might end up with like say rough surfaces or smoother surfaces like you can see here, and with larger grain boundaries or like super small columnar boundaries like shown here. To show you like a couple of my own research results from a few years back. So we were working on some solar cell for fabrication. Solar cells, you know, they absorb the light, you send the light from the top, and then some of it gets reflected. So this is an actual simulation result, by the way. And some important portion of it is leaking into the absorber material. And the idea is, of course, to absorb the incoming light. This is showing you the intensity of the light. So we're kind of exponential decaying the intensity, like you guys can see here. So at some point here, we kind of kill or annihilate all the light's energy intensity, and then we absorb it completely. That's another way of saying it. So for that, we were not using a flat solar cell, but we were using a like these kind of formations, these kind of nanostructure formations, like you guys can see. And to do that, we had to sputter coat these dome structures. This is like from a cross-sectional view with a sputter coater. What happened is you cannot really, as you can see, that's the bad side of sputtering. It's very difficult to get a good conformal coating. The step coverage or the conformal coating or the thickness of the deposit material on the flat surface with respect to the sidewalls is not the greatest with sputtering. That's kind of generally the case with these physical vapor deposition tools. And you see, we haven't been able to cover like this area here. But I will show you like next week, actually the other week after next week, with the atomic layer deposition that we switched to back in the day, aluminum zinc oxide with the, now it's not coated with silver, but aluminum zinc oxide, these little dome structures. And we switched to atomic layer deposition. And in that case, when we have atomic layer deposition, you see that the we've got a really conformal coating, meaning again the height in the sidewalls and the planar surfaces are equal to each other. All right, so this kind of completes this, but before I leave the floor to Rich for the last half an hour or so, I will again show you what we are going to be doing with Rich together in the hands-on part very quickly. As we were saying, with the sputtering, we're generating the plasma, we're attacking the target with the ion, and then we're knocking off some particles, and those are going to the substrate with the help of diffusion. And what Rich is going to show us is a gold deposition, gold sputtering deposition, but we're going to do it for an extreme case. We're going to do it for a very, very short time, okay? And for like 10 seconds or less. And in that amount of time, we'll not be able to cover the whole surface like equally. Instead, these are like, say, could be like your gold atoms. We're going to cover some areas more than the other, and we're going to generate these kind of island sites. Okay, islands will be formed, and we're choosing a noble metal, gold, for a specific purpose. Because gold as a noble metal will not do some good adhesion with the substrate, that's going to be glass, will not bond to the glass efficiently, and gold will not stick to wet the surface of the glass, in other way of saying. So in other words, it's kind of going to be like easy to migrate gold on the surface. So the gold will be able to diffuse easily on the surface, okay? So we're going to sputter coat very quickly, and we're going to try to create these nucleation sites after giving the heat. So we're going to deposit with gold on the glass surface, and then we're going to give a little bit of heat. And after the heat application, you're going to see that the deposited gold on the surface will start to create these little bit of larger particle sizes like shown here. And those larger particle sizes will come to a uniform nucleation size with certain nanoparticle sizes. And that's going to be the stable condition. And I kind of did that with my students here. Let me show you the results. And we got it from, remember from last week, we did the atomic force microscopy last week by using the atomic force microscope like shown here with a tip. We kind of scan across the surface. We were using a tip there. And my students 2 summers ago did a similar thing. We did gold deposition, sputter coat deposition on a surface of a glass layer. And right after the sputtering, this is how it looked like. This is like 8 seconds of sputtering under atomic force microscopy. So you're seeing some hills and some darker areas where gold is not really too much found there. And when you take a cross section with an atomic force microscope, you see the structures, the hills, like you guys can see, and the width is like 250 nanometers. It's a large structure like you guys, but this is kind of like random structure appearing. Now we're going to put it on the hot plate and we will anneal this surface. And after the anneal, this is what Rich will show us. We will form these more homogeneous structures with a homogeneous nucleation site and accordingly homogeneous diameters in terms of the sizes. And when we take the cross section, we will see that these little dome structures are going to be found on the surface with the more regular size in the cross section, like 20 nanometers or so. So the gold will migrate and will form these kind of surfaces. And once you do a numerical simulation of an optical simulation of these structures, when you send light from the top surface, okay, and there's gold on the substrate here, okay, you're sending the light and looking at the light transmission and comparing that with the initial structures where you had like covered the whole surface area, not like this. You don't have this structure. You have this more smaller dome, uniform dome structure after the anneal. This is like before and after case. And you see that after the sputtering, right after the sputtering, you see the structures, the glass slide getting in the simulation results and also in the measurement results, UV-vis spectrometer measurement results, they're absorbing more of the red part of the spectrum. This is the red part of the spectrum. We absorb more there. But once we do the anneal, we get like smaller dome structures, and then we start to absorb like shorter wavelengths. And you immediately see that the simulations will show you absorb green part of the spectrum. That's corresponding to 500 something wavelength nanometer size. Okay. And that's why after and before and after the sputtering, Rich will show us that before we have like right after the sputtering, we will end up with like this bluish color of the glass, because we just sputter coated the surface. We have like some random structures of gold creating island formations. And when we look at the spectrum, they absorb the red part of the spectrum, like 700 nanometer red part of the spectrum, okay, right after the sputtering. So they absorb the red, they don't absorb the green, that's this part, they don't absorb the blue. So that's why they kind of shine, reflect back the color as the colors that are not too much touched, and those are adding up to this interesting color, the blue and the green, but mostly like green also coming into play. So as for the other one here, right after the anneal, we form these dome-like structures, uniform dome structures, and we absorb the red colors anymore, but we touch and absorb more of the blue, green colors this time. And we're also absorbing quite a amount of the blue colors too. So the whole thing turns into red colors, because all of a sudden, because of the gold migration on the surface that we call the nucleation, then we start interacting with the green part of the spectrum instead of the red part of the spectrum. We see that in effect in even like the gold nanoparticles from the Faraday's, Michael Faraday's first experimental nanoparticles. You can synthesize them in the nanoparticle, like colloidal solutions too, like probably a lot of you guys are familiar with. They're kind of like little nano antennas and resonating with the incoming colors, incoming radiation from the outside. I'm just gonna super quickly show you one last thing and then leave the floor to Rich for the hands-on. So look at the timer too. Okay, so the Nanosphere Labs. So there's this website. Please go to NanoHub. They have splendid, good simulation tools there. Nanosphere Optics Lab. So I'm just clicking on it after getting an account and clicking on launch tool. This is all free after getting an account. So you can use that with your students too. So this is just simulating a gold colloidal solution, but I mean, you can do silver as well. But anyways, so if the particle radius is 20 nanometers, if this time we're not doing it with sputtering, but in a similar sense, if the result will be in terms of the spectrometer, the results, you absorb the highest resonance. This is the localized surface plasma resonance in the fancy way of saying it, but just the highest absorption, let's call it that way, will come around 510, as you can see from the chart here. But if we do it for a larger, like say 50 nanometer, and let's resimulate that. So we did this for 510. Now we're doing a large particle and it becomes 521 nanometer. All of a sudden you see this highest absorption. So based on the different sizes, the larger sizes will start to go into the red part of the spectrum. That's why Rich's first sample will absorb more and more the reddish part of the spectrum. So it's going to look more blue for that reason. And you can, yeah, I like to use the simulation tool. I would encourage you guys to do the same. So I'm stopping sharing my screen and letting Rich take over.
Okay, so this is our Leica Ace 600. I have it already under vacuum, and as Ozgur said, I have 2 slides in there. One slide, we're going to show you both slides. We're going to show you the one slide after we do the nucleation and what the slide is when it comes out of our sputter coater. And all I have to do here is we have a screen on our thing, and here it's all software driven, this Leica. So this sputter coater is all software driven. I have gold target in there. I have it set to put approximately 3 nanometers down of gold. And all I got to do is press start because it's under vacuum already. And the process should start going. Let's hope it registers. Yes, it's doing its purge cycle now. So it's doing a purge cycle to get us a nice clean in there and mix our gas up a little for us so that when we get started, everything, the pressure will drop to where it needs to be. And then the pressure will give us our plasma, as you guys been talking about, and we will be sputtering our gold. This system here, this Leica, it has 2 heads inside. One, we can put targets in to sputter various metals. We usually do gold, palladium inside this machine, but we also have gold target. So I have the gold target in there now. But this machine also will sputter, or actually deposit, carbon. So it'll deposit carbon with a thread. We have a carbon thread that we thread inside the Leica here. Then we close it up, put under vacuum, and then it will send a charge through the thread, causing it to flash. And when the thread flashes, it rains the carbon down onto our sample. So right now it just switched over to waiting for our turbo pump to slow down so that it can get to a point so it can acquire our proper pressures. So this machine is nice. Like I said, it's software driven. So you just set your recipe up and you go. So that's kind of a nice little feature of this. I know there's one thing Ozgur wanted me to show you guys. I think we have time to do that, is I'm going to show you a target that we used in here in this machine and the type of pattern that it makes.
Right, so we didn't have too much of time to talk about it, but you guys can see that the ions have attacked certain regions on the target material. What was this, palladium? No.
Yes, gold palladium.
Gold palladium, right. So especially this is a big problem when you have magnetron type sputtering. The ions over and over under the influence of the external magnetic field attack certain regions and leave these kind of damage zones behind. Yep, thank you.
Okay, it's getting ready. As you can see, the stage has risen to get us up near our plasma, and it is trying to ignite it, and I think it's been successful.
Right. Yes, we can see the color. This is the glow, plasma glow that we were talking about. So those are the excited argon atoms, not fully ionized. And depending on the color, especially like when I'm inside the clean room, people can immediately tell, okay, so this is argon plasma, this is fluorine plasma. I'm not at that level, but it's not so difficult either. But yeah, they give you different colors, very distinctive colors.
Okay, well, it finished putting down 3 nanometers. Now it's venting. What's nice about this system is it vents really nice and quick because it's all automatic. It's got all these solenoid valves inside. So all of our other systems in our clean room here at SUNY Erie takes time because we don't have all the same kind of venting possibilities. But this system is great for that. This system is our typical system for putting thin layers down because it's kind of a system that's more or less designed for sample prep in a lot of cases, and that's what we use it for, sample prep for our scan electron microscope. So when we do nice thin layer, this works great. All right, now I'm going to get this puppy back down to where we need it. Okay, so now it should drop my stage back down for me. Get it all reset for another process while I'm doing the vent here. And then we're gonna take it over and we'll place it on the hot plate at about 420 for about 30 seconds. And then I will show you guys the results. Hopefully, this is kind of a small chamber. Those glass slides aren't super small, but we should be good to go. Looks good from here so far. So when we get that puppy thing, when we get that open, we'll be all set. Let's see, this system, I don't know if there's much else I can tell you about it. You can see the inside, it's all automatic. You can see that I was on the right side. That's where the target is. On the left side is where we can do the thread. I can show you the thread. I have it right here. I'll get just a piece of it dangling. If you can even see it coming out of here. So it's just let me get it over where it's clearer there. So it's just a thread. We thread it on there. It's not a strong thread. It's pretty thin. It's not super thin, but it's not strong. So when you thread it into the system to get it ready, it goes around 5 screws in a weaving type pattern, like a sawtooth. And then so it has each of those threads, it fires off so many times to deposit our carbon onto a sample for us. This system here, I want to say, if anyone was curious about cost, I want to say I think it ran us around $35,000. And this was probably about 5-6 years ago. So I'm sure it's a little bit more. This system can also be expanded for cryo purposes, and also I think for a chamber, so that you can have a bypass chamber or a chamber so you don't lose your vacuum. Those are all add-ons. It's almost done.
Rich, what did you say? Which company was it?
This is Leica.
Oh, yeah.
Leica, Leica Ace 600. All righty. Let's get it out.
Now, the first thing that students immediately are kind of shocked about is, hey, why is this not golden color, right?
Yeah.
Yeah, so if you can put that's great. So with the white background, we can clearly see this bluish color that I was referring to, and that's all coming because of the bigger metal island optical light interaction.
Okay, let's do this. I don't want to make anybody dizzy, but I'll take this over towards the hot plate, and we can do everything over there.
Yep, the next annealing round. By the way, in this lab experiment, we use also UV spectrophotometer and also atomic force microscopy. And Rich these tools in their lab too, but due to time restrictions, of course, this is like a full-fledged 4-hour lab, by the way, to do all these things at the same time, to synthesize the nanoparticles, gold nanoparticles. So he's putting it on a hot plate that's above 400 Celsius degrees on a hot plate here for like 30 seconds.
Yep, I can see that visually from my end. I can see it changing color already.
Yeah, we have the nucleation taking place. So thermodynamically, the gold is migrating and driving to become more uniform, but smaller in size. Its aspect ratio, what I mean is its height is getting larger with respect to its width. and that will change its light interaction property. So we will see different color getting reflected.
Let's
from the
see if it comes up
Yep.
good somewhere here.
Perfect.
Let me turn
perfect.
it.
Yep. Perfect.
So we can see that.
Mhm. Could we see them at the same time, or is it too difficult to hold together?
Nope, we can.
Yeah, that's the one before, after the sputtering, but before the annealing on the left-hand side. And that's after the annealing on the right-hand side. This is the clear exhibition of the localized surface plasmon effect. As the size of the gold nanoparticles are getting smaller, but more uniform on the surface, we start to absorb more and more the shorter wavelength colors and reflect more of the bigger wavelength colors. That means we're reflecting more of the red part of the spectrum and eating away less of the, eating more of the green part of the spectrum. And that's the UV vis, right?
Yep, right in the middle.
And right behind that is your AFM, atomic force
And then
microscope.
here is the AFM. That one, it's a Bruker multi-mode 8 AFM. And the UV vis is a Perkin-Elmer 1750 Lambda, I think it is.
Yep.
I believe if you wanted to purchase a UV vis like that one, I think that one was about, if I recall correctly, around 50, 60K. And the AFM, the multi-mode 8, that ran us a little over 100K for those two instruments. And you just got a quick little tour of our clean room also. We have a 1,200 square foot, basically teaching clean room, similar to what Penn State has. We have a whole bunch of equipment in here. I want to say about $1.5 million worth, around $1 million worth in that neighborhood. That works great, mostly characterization. And I think that concludes, unless there's anything else, Ozgur.
Yep. Perfect. Yeah, thank you very much. And we will be together, Rich and I, again in the week after Terry's presentation on CVD. We will do ALD together with today's discussions and the slides, the PDF files, etc., the supplementary materials from last year, also the simulation tools that I was using. Do you have any questions? And I think we have like 7 minutes in here, but we also have the office hours like announced on Canvas. Mine will be Wednesday afternoon, 5 p.m. Eastern time. So I would love to discuss more in depth a couple of things that we covered here, if you have time, of course. That's about it.
Thank you.
Yeah, absolutely.
Thank you. Great simulation and great demonstration. Thank you.
Thank you. Thank you, Greg. Yeah. Yes, thank you, Remy. So hopefully see you guys for next week and upcoming weeks. Bye.